And we're back. Welcome back and happy Thursday. Today we're going to switch gears a little bit and talk about yet another feature selection and dimensionality reduction technique, namely locally linear embedding. But before we begin, some administrative bits. Now, there are a number of papers on LLE, and the ones in particular that I will direct you to are the following. The first one from NYU is by Sam Ruiz, who co-created LLE. It's introductory in nature. And then the other one is more comprehensive by Saul, and it is a complete account, including some of the numerical issues. Now, the second paper from Gemler, Journal of Machine Learning Research, I don't expect you to read all of it, but certainly most of it as a guide for some of the backstory behind the more summary type explanations that are in the first paper. There is a great online video that takes a very rigorous view of what LLE is doing. And also optionally, you can look at this last source, which is the first 40 minutes of that video on YouTube, and it explains from topology some of the background behind LLE and embeddings and manifolds in general. Okay, so let's begin. When we last left off, we talked about recovering a low dimensional embedding from a higher dimensional representation. And for this, we looked at nonlinear manifolds, specifically the three-dimensional spline and the Swiss roll, and we talked about the axes that define the measurement types or directions in which various features changed. And we said that you can reconstruct this in a lower dimensionality. And of course, in machine learning, we know that if you can represent things in lower dimensionality, your generalization or your performance will be superior. We talked about Isomap, and we said Isomap uses so-called geodesic distances. You traverse a tour, as it were, in the k-nearest neighbor graph to construct distances pairwise between the data points, which are considered samples on an underlying manifold, and the distance then between vertices or these data points respects, when you do this, respects the curvature of the shape of the manifold. We then talked about multidimensional scaling, and multidimensional scaling used relative position or differences between a data point and all of the data points in your data set. Now, Isomap is an extension, an improvement, as it were, on MDS, multidimensional scaling, but multidimensional scaling has very useful as it comes up, or you can comprise by diagonalization of this dissimilarity matrix, come up with a lower dimensional representation that respects this relative information, this dissimilarity between the data points. So today we're going to talk about locally linear embedding. And before that, we look at a typical manifold, and this toroid, donut, if you will. It's a data point, and its neighbors are said to be locally linear. They lie on a linear patch of this manifold. And so if you take a particular segment on this manifold, and that's the black point, and if this patch is small enough, then all of its neighbors are going to be on some linear surface. So in essence here, you have a 2D projection, and on that two-dimensional surface, you're representing some small region of this three-dimensional shape. Now, here's the data point, and here are all of its neighbors here in red. And so this idea of local linearity is exploited in a very clever way in LLE in order to characterize the shape of this manifold, the curvature or the details of the surface of this manifold. And so the idea then is to try to take the relative relationship, the neighborhood information, and project it down to a lower dimensional representation. So we might go from 3 dimensions down to 2 dimensions, or 5 dimensions down to 3 dimensions, and you want to project it in a way that you preserve the neighborhood information. So in essence, LLE kind of bears some similarity to multidimensional scaling. Multidimensional scaling strive to project their data, the data, down to a lower dimensional representation so that you respected the relative relationship between the data points. And for MDS, it was the dissimilarity matrix between all the data points. Now, in Isomap, and LLE kind of bears some resemblance to Isomap in that you want to have some kind of representation of the geodesic distance between points. And so how we're going to do this is by maintaining a property, and that property is going to look at the relationship between a point in the center, some x, and all of the points nearby it. But if you assemble enough of these small two-dimensional patches, you can represent very nicely the surface of this manifold. And you can do so in a way that you're not calculating a lot of pairwise distances between your data points, because if you do that, you might have a large data set, and it's going to take a long time to compute this dissimilarity matrix, and it's also going to take a long time to diagonalize it. Likewise, for Isomap, if you have a k-nearest neighbor graph, you're going to have to run Dijkstra's algorithm on that k-nearest neighbor graph. And what happens if you have a really big data set? Well, your k-nearest neighbor graph, when you run Dijkstra's algorithm, it's going to take a long time because you have quite a large k-nearest neighbor graph. So let's look at this local linearity property from the perspective of LLE. So if you have a linear patch, if it's small enough, regardless of how curvy or how bumpy the manifold is, if that patch is small enough, it can be approximated as a linear surface. Now, as a linear surface, what that means is that you can describe then the points on this patch, let's call it the center point, as a combination of its neighbors. So that means if this patch is linear, it's a two-dimensional surface, we can absolutely define the center point, let's call that x, in terms of all of its neighbors that are around x, if they're close enough, if this patch is small enough. So let's work with this, and let's first talk about this idea of a tangent space. Now, here is a curved surface. You could think of this line here as a manifold that's in two-dimensional real-valued space. So this is a manifold in R2. And so the idea then with a tangent space is to look at all of the tangent lines associated with every point on the surface. So here's a tangent line. It comes into contact with that manifold at a single point, and it exists at some slope relative to that approximating surface. And so that tangent line you could also think of as the slope of that manifold at that particular point under consideration. And so if we were to take the tangent lines going across the entire linear surface, and this is a linear manifold, nonlinear manifold, and each one of these points is going to be a point on that manifold, and then each one of these line segments, that's a tangent to that manifold at the point of interest. So we have a tangent line here, tangent line here, tangent line there. And if you look at the collection of tangent lines, they each have an angle, and they have association with them a point on the manifold. And the collection of all the tangent vectors together describes the shape of this manifold. And this construction has a name. It's called the tangent space. It's a tangent space of this manifold. Okay, so if we think about what a tangent line is on a so-called one-dimensional surface, it's a line. But if we think about the tangent on this three-dimensional surface, you can imagine here's our manifold M, and we take a point on the manifold, we'll call that X, and we draw a tangent. And that tangent is a plane. It's a linear patch, just like a line is a linear patch, but this tangent to this manifold in 3 dimensions is this 2D sheet. This is 2 dimensions. And if you think about it, it's at certain slope relative to that manifold, and it touches the manifold at a single point, and we're going to call that point X. And so if you look at this tangent here, there are many vectors that you can draw that are tangent at the manifold at point X. Maybe there's a vector going in this direction. Maybe there's a vector going in that direction. Maybe there's a vector in that direction. And the one given is that each one of these vectors make the same angle with respect to that point x on the manifold. And so all these vectors will fall in the sheet because they have to maintain the same angle in order to be a tangent line at that point on the manifold. And so if we take a look at the sphere, in this depiction, we have a bunch of tangents to the manifold, which is the sphere, and it doesn't draw in all of them, but it's enough to kind of give you a sense of what the tangent space would look like for this particular nonlinear manifold. And so here is an example of a manifold. We have our nonlinear curved surface, and let's add in an additional constraint that is differentiable. This manifold is differentiable, meaning that the derivative or the gradient at any point along the manifold is defined. Now, of course, in order to have a tangent space, you have to have derivatives, and therefore it makes sense that this manifold would be differentiable. It's nonlinear, but it's smooth, i.e. it's differentiable. Okay, so let's define a point xi on this manifold, this nonlinear manifold, and now we're going to look or consider the idea of local curvature. So we have the tangent space associated with a particular point, and now I haven't made any distinction about which point xi on the manifold this is. So you can imagine a whole lot of other tangent planes for each point that you have on this manifold, but it only makes sense for teaching reasons to draw a single tangent plane associated with a point on the manifold. And so now we want to measure this idea of the shape of the manifold, and we're going to use this tangent plane in order to define for us this idea or metric for shape. And that shape in this local patch on the manifold associated with the tangent plane is going to give us a way of characterizing or measuring the curvature of this manifold. How does it bend? How does it twist? How does it turn? Is it smooth? Is it bumpy? Does it slope? Does it slope a lot? Does it slope up? Does it slope down? Etc. So let's define a small patch around that point, and that patch you can imagine is being on the tangent plane, and we're going to call that the neighborhood associated with that point on the manifold. Now, of course, if this manifold is highly nonlinear and it's very curvy, as long as we make that patch smaller, so I could make it really small, we can approximate it as if it were a linear surface, this 2D plane that is tangent to the manifold at that particular point. So it doesn't matter how curvy or what the shape is for the terrain of the manifold. If the patch, this neighborhood, is suitably small, then we can approximate it, and for all intents and purposes, it is a linear surface. In 2 dimensions, it would be a plane. Okay, so we have our neighborhood, and we're going to define Ni as the neighborhood for point xi on the manifold. So now we're going to define a bunch of points, x1, x2, x3, and so forth, and these points are going to be neighbors within the neighborhood. What do they mean by that? That these points, x1, x2, are going to belong to the neighborhood that's small enough, that local patch around that point xi on the manifold. So in essence, we could treat these points, x1, x2, x3, and so forth, as if they were on that linear surface, that sheet, but they don't have to be on the sheet. They might be a little bit below the sheet, a little bit above the sheet, but that patch, that neighborhood around xi is so small that it's not too much different, all of these points, relative to the position of xi. You can effectively treat them like they're on that sheet, but they're not always on that sheet in reality. Now, we take our neighborhood of xi, ni, and we're going to use index j to refer to those points that are in the neighborhood of xi. So we're going to use j to index our x points, which are the neighbors that are in the neighborhood that patch around xi. So now what we're going to do is we say, okay, well, if these xj are really, really close in the neighborhood to xi, and they're approximately on this linear surface, this sheet approximating this small region of the manifold, then because it's on a linear surface, we can actually describe xi in terms of all of those points around it, and that description is going to be a weighted combination. And so this idea of this weighted combination of each one of those points in the neighborhood around xi, we're going to use the weights to reconstruct xi from those points in that patch, that neighborhood around xi. And that set of weights, that linear combination, is going to be a measurement of the shape or the local curvature of that particular small patch around that point, which is tangent, or on that point on the manifold through which or at which that sheet is tangent, i.e. the tangent space for that particular point on the manifold. All right, so let's consider what that reconstruction weight would look like. And so we have our linear approximation, and then we have our points that are considered not far away from the tangent to xi, and then we're going to compute. So here's our tangent to xi. That's our tangent. And we're going to take our points, which are not very far away, and we're going to treat them, because they're so close to xi, we're going to treat them as if they were on that sheet. And now we will reconstruct xi by some weighted combination with each one of these j data points. And so here in this figure, we're only showing two. Xj is in the neighborhood of point I, and xj prime is also in the neighborhood of xi. On the previous slide, I drew x1, x2, and then generalized it with xj. Now, these are all points within the neighborhood of xi. And because they're really, really close, that difference is not very much between where xj and xj prime are in reality on the manifold. And so they're so close and not that different, we can say, well, it's on the same sheet, and we're going to treat it as on the same sheet, and that sheet is linear surface. So we're going to say xi is constructed by this weighted combination of each one of these points xj from the neighborhood ni. Now, of course, there's going to be some reconstruction error. That's this amount. This is the reconstructed point from the weighted combination, and this is our reconstruction error. So there's a little bit off, but nonetheless, if we choose our neighborhood to be small enough, this patch around xi, this reconstruction error is going to be close enough for our purposes. Now, this weight matrix, wij, it consists of entries, and the wij, the jth entry of this vector, is going to be the weight that is counted as that particular combination of xj within the neighborhood. And so wij is a weight vector, and this weight vector for the ith vector is the weight vector for xi using a linear combination of all the j xj's that are in the neighborhood. Now, of course, if you have n data points, the xj entries corresponding to the neighbors of point xi, those are going to have non-zero values, and those points from your data set that are not in the neighborhood of I are going to have zero values. So you can think of this as a weight matrix and achieve that same purpose. It's zero for all of those points that are not in the neighborhood of point I. And so you can have this vector of a rank corresponding to all of your data points, and many, and you can put them together in a weight matrix and have a linear system describing all of the weights for all of your data points xi with respect to their neighborhood weights with the xj neighbors around them. So you take these linear approximation patches and you have a weight vector associated with this point xi, you have another weight vector associated with this point x, so I maybe call it xi prime, and then this one xi prime. Now, of course, I can't draw all of those patches, those linear surfaces, tangent to every single point for this particular manifold, but I've just drew a couple of them to give you the idea of what LLE is doing. And so if I do this linear approximation for every single data point, I'm going to have a lot of these facets that together, the set of weights for this patch, for this patch, for this patch, together are going to define the local curvature for that patch or that region in the manifold. So in essence, what we're doing, kind of like Isomap, we're looking at some characteristic of the local neighborhood, and then kind of like MDS, we're considering what that neighborhood looks like globally across the entire manifold, but in this case, across all the data, but in this case, we're doing it by assembling all of these patches together across the entire manifold. And so we're looking at a global description of the relative relationship across the entire data set, just like MDS, but we're doing it using a local description across small regions of the entire manifold. So it's like a local description. We're doing it globally by considering multiple local regions globally across the entire surface of the manifold. All right, so let's take a look at this idea of what we do when we project. We're going to project our data down to a lower dimension, and we want to do so such that we preserve the neighborhood structure. We preserve this measurement of curvature. And in this case, this curvature is going to be represented by that weight matrix. And that weight matrix, as we said, that weight matrix is going to choose the weighted combination of the local neighborhood that best approximates the original point on the manifold xi. And so if we do this, preserve this weighted combination of the neighbors, we're preserving the weight matrix of this patch, of that patch, of that patch, that patch, each weight vector or the weight matrix associated with all of the patches around every data point on the manifold. And so we start out for each data point xi, we select all the neighbors that are closest, and we're going to measure closest using k nearest neighbor. And then we're going to reconstruct the points xi through linear combination of their neighborhood. So here's xi in the center. Here's my weight vector that sums together xi with each of the j neighbors. So there's xj, xk, xq, and so forth. And then once we get that weight matrix that reconstructs the original data in terms of a weighted combination of their nearest neighbors, we're going to map to a new set of coordinates. And that new set of coordinates is going to be of a lower dimensionality than the original representation for our x data. And we're going to map it such that we preserve these weight vectors. And so the relative relationship between each point in the original representation and all of its closest neighbors, that relationship is going to be preserved, but we're going to do so carrying this relationship to the new representation using a new set of coordinate axes. So that's what LLE is doing. It's combining this idea of relative relationship across all of the data, like we saw in MDS, but it's doing so by assembling a bunch of local relationships, one small patch or neighborhood at a time. All right, so we have our d-dimensional data, and that's original representation, and we have big N many data points in d-dimensional real-valued feature space. So we have d many features. And the idea then is we want to compute a k-dimensional projection, and k will be of a lower rank than d, lower dimensionality. And we're going to compute these projections such that for the first point x1 in d dimensions, we're going to have a k-dimensional point z1. For x2, we're going to have a k-dimensional point z2. and so forth up through xn. We're going to have a k-dimensional projection zn. So there's a correspondence here between the original d-dimensional feature vector. There is a k-dimensional feature vector. And this kind of relates back to this idea of a phi function that we talked about. It's a mapping, it's a projection. We're changing the dimensionality, the basis that we're going to use to represent each one of these points. But we do it so that we preserve all of the local neighborhoods around each one of the original data points. And we're going to use the reconstruction weights, these weighted sums, in order to do that. So let's take a look at it. So the first thing we're going to do is we're going to find for each data point the nearest neighbor. So we're going to use the k-nearest neighbor algorithm. And we're going to find the L nearest neighbors, but our requirement is that the number of neighbors, the neighborhood size, has to be greater than the dimensionality in the reduced representation. Now, the reason for that is as follows. Suppose we have a three-dimensional space, and we have a point, let's call that xi, and xi is in 3 dimensions. And so we're going to project that into the first dimension. We're going to call that x1 hat. We're going to project that into the second dimension, call that the x2 hat direction, and we're going to call the third dimension x3 hat. Now, if we were going to reconstruct xi from some other set of points, if we only had 2 other points, let's call that xq, and let's call that xw, and we want to reconstruct, well, if we only have 2 other points to reconstruct, it's very likely we're going to miss one of the dimensions. So if I look at this reconstruction, well, that's just an interpolation between xq and xw. And so it's some weighted combination between xq and xw that just gives us some position along this line that pierces this point xi. In order to fully represent this reconstruction, because remember, we're talking about curvature, we need at least one more point than the new representation. Because if we don't have that one more point, and in this case, my representation, if I want to reconstruct this in 3 dimensions, well, I can't possibly represent something in 3 dimensions if I only have an interpolation that's a two-way interpolation. I just can't do that. If I had another point, xv, now I can treat this position as some combination with respect to this point and that point. You could think of that as one axis. And then this point and this point, you could think of that as another axis. And you now can do this reconstruction because you have some difference along x, some difference along y, and you also have some difference along z. Or more correctly, I should say, you can represent with 3 points a difference with respect to the x1 hat, a difference with respect to x2 hat, and a difference with respect to x3 hat. You have enough degrees of freedom, ways to move the location of the reconstruction along this direction, that direction, and that direction. For this reason, you need the number of neighbors to be at least, or the dimensionality of the new representation. So if we're going from R super D, our original d-dimensional representation, and we're going to map that through our phi function to R super K, your L for the number of neighbors around xi has to be at least x1, xk. It has to be at least that in order to reconstruct that xi as a weighted combination of all of the xj in the neighborhood around xi. And this is ni, the neighborhood around xi. Okay, so for each data point in our data set, we find the L nearest neighbors, where L, the number of neighbors, the neighborhood size of the neighborhood around each of the data points, is at least k plus 1, where k is the dimensionality of the new representation. So now we're going to assume that each one of our data points from our original data set is a weighted combination of these L nearest neighbors. So that means that point xi is approximately equal to each of the xj's from neighborhood I, that's the neighborhood of xi, weighted through some weight, right? Okay, so again, Each of the entries corresponding to a neighbor are going to be non-zero, and each of the entries corresponding to a non-neighbor are going to be 0. So we're going to find these weights using least squares fit, and we can actually do this quite easily. It's a quadratic optimization problem, and we can actually solve this through matrix algebra using Lagrangian optimization. And so our best W is going to be the set of weight entries across each one of our data points, xi, that minimizes the norm squared of the residual difference. And that residual difference we're going to call our reconstruction error. Reconstruction error. And this reconstruction error is the difference between each data point xi and the weighted sum of those neighboring points in the local patch around xi. Now, if you notice here, we'll make a few observations. Well, xi, these are constants. xj, those are constants. These are given to you, they're feature vectors. And so the only term we have here that is variable are our weight entries, and it's squared. It's a quadratic optimization problem. And so we can actually solve for that using Lagrangian optimization. And now we're going to make a little bit of a constraint here. And the constraint we're going to make has to do with the fact that these neighbors, xj, are close by xi, and we want to enforce that they're close by, and they're a linear combination, and they're not too big, these weight combinations. We're going to enforce that the sum of all the weights are equal to 1. So this makes it a so-called affine combination. And so what we're going to enforce is that for every xi, the neighbor weights that are going to try to reconstruct the xi are going to sum to 1. So we're going to set that constraint. And the good news is that's an equality constraint. So we can absorb that with a slack variable and solve this quadratic optimization problem as an unconstrained equivalent using matrix operations. All right. So this is the first thing we do. We find all the weights, and these weights collectively are going to describe the local curvature, the shape, if you will, of the local patches around each one of these points xi in their respective neighborhood. All right. So now we're going to compute the low dimensional projection. So we're going to go to a new representation, and that new representation is going to have a dimensionality of rank k. And we're going to solve that by carrying over these reconstruction weights. And so we're going to preserve the curvature of the local patches around each point, but now our points are in k dimensions. So what do? We choose our new value of the data points such that across all the new values of the data points in dimension k, we're going to minimize the reconstruction rate, the reconstruction error. So here we have the reconstruction error, and that's reconstruction error is just the difference between each new projected point and the weighted combination with its neighboring points. And we're going to do that for every single point in the smaller representation. Now, if we look at this, we're going to make an observation. Now, this weight vector, that's a constant. And that constant is exactly the solution that we got before. Then we said before we can solve for this because the only variable we had was the weight vector, because the x's, those are all constants. And we can solve this as a quadratic optimization. Likewise, here we have variable z and variable z, all of our new point representations. Those are variables, but this weight vector, this set of weight vectors describing the curvature or the reconstruction weights, if you will, those are all constants. So here in this quadratic, because it's the norm squared, we only have a single variable. These are the zi, the vector values for the individual data points. Now, of course, we're squaring and we have a sum, but we can actually take the gradient of this with respect to each one of these points set to 0, and we can solve. We can also solve that as a quadratic optimization problem. So we do this, and we're going to add some constraints. We're going to make the assumption that in the new representation that the data sums to 0. That means these vectors are centered. And you can get centered vectors. One of the ways you can do it is through some kind of orthonormal decomposition like an eigen, but we can solve this quite easily with another quadratic optimization solver. So now we're going to choose a low dimensional point that is best reconstructed that satisfies this equation, the reconstruction error, given the same curvature measurements, reconstruction weights that we solved from the original data. We're going to choose our new value for each data point such that we minimize the reconstruction error. And we're going to reconstruction error respecting the same curvature that we calculated when we had our original data in our original representational space in D dimensions. And so this first constraint says that these vectors in the new representation, they're centered, right? So they have a nice property that they're centered about origin. And then this other property that we're going to set is that the covariance matrix in the new representation is going to be identity. It's going to be diagonal covariance. And what does this mean? It means it's full rank. We're going to have all k dimensions. We're not going to lose rank. In addition, it's going to have a nice diagonalized type of representation. And so now we're going to choose the low dimensional points that best represents the reconstruction weights from the original representation. And when you use the same reconstruction weights from the original representation, you're also maintaining the same curvature from the original representation. And so that is what locally linear embedding does. And we will revisit this, kind of tinker a little bit to show you the impact of what LLE can do for you. Now, we have these constraints. We also, as a parameter, we have k, and we said k is the rank of the reduced dimensionality. We go from R d-dimensional to R k-dimensional, and we said the number of neighbors in the neighborhood, the size of each neighborhood, we said has to be greater than or equal to k plus 1. And so those are restrictions that are imposed by LLE in order to produce a lower dimensional representation of your data while still respecting the curvature globally and locally of the underlying manifold. So with that, we'll end there, and I will see you all on Tuesday. Until then, as usual, please stay healthy, stay safe, and have a great weekend. I will see you Tuesday.